The last thing for this week is looking at concavity and the second derivative. Again, this is stuff that you learned last year, so this is just a quick refresher, but we will see how this plays in with parametric and vector curves here. So remember that with concavity, the idea is that if the derivative is increasing, meaning the slope of the tangent line is getting progressively steeper and steeper, that means that the function is concave up. If the direction of the tangent line, the slope of the tangent line is getting more and more negative, steeper in the negative direction, then it is concave down. You can remember concave up looks like a U, concave down looks like a frown. Okay. The test for concavity is to look at the second derivative. The second derivative is going to be greater than 0 if we're concave up, less than 0 if we're concave down. The same idea applies. You're going to look at critical numbers of the second derivative. They're not really called critical numbers anymore when you look at the second derivative, but just like with the first derivative, when we find critical numbers, for concavity, the possible points of inflection are going to happen where f double prime is 0 or where f double prime is undefined. So then you're going to test intervals just like you did with extrema, okay? So let's do this first problem to refresh our memories here. All right, so for number 1, I'm going to do this one very quickly so that we can get to some of the other ones and keep this video a little bit short. We're going to start by finding the second derivative. Then we're going to test some intervals where that's equal to 0 or undefined. All right, so the only critical number we end up with, again, I keep saying that, it's not really called a critical number. The only possible point of inflection that we have is x equals 0. We're testing now in the second derivative. If I test negative values, I get negative for the second derivative. Positive values, I get positive for the second derivative. So that tells us that this function is concave down on the interval from negative infinity to 0, and it is concave up on the interval 0 to infinity. Okay. I want to move on to the next one because it's a little bit uglier. This is where, if you remember from last year, we have to kind of take the domain of our function into account. This derivative does not end up very nice, unfortunately, but this is some good algebra for us to look at. So the first derivative is going to need a product rule including a chain rule. We want to think of this as x times 9 minus x to the 1/2 power. Here we go. There's a little bit less room here than I would like, so you might want to write kind of small. So the first derivative, f prime of x, is going to be the derivative of x, which is 1, times g left alone, 9 minus x to the 1/2, plus the derivative of g, which is going to be 1/2 times 9 minus x to the negative 1/2 power, times the derivative of the inside, which is negative 1, and then times f left alone, which was x. So, looking at what I have here, what I have in common that I can factor out to make my life easier is I have a 9 minus x. I'm going to take out the the lowest power, which is negative 1/2. I'm also going to pull out this 1/2 right here so that I don't have the fraction on the inside to take care of later. So what I'm going to factor out is I'm going to factor out 1/2 9 minus x to the negative 1/2 power. When I do that, remember we subtract exponents. So 9 minus x to the 1/2 minus 1/2 is 9 minus x to the first. So that's just a 9 minus x. But we also factored out the 1/2. 1 is in front right here. 1 divided by 1/2 is going to be 2 times 9 minus x to the first power. Out of the next one, we factored out the 1/2. We factored out the 9 minus x to the negative 1/2. We're left with minus x. And so our derivative, I'm going to kind of sort this out now. In the denominator, I have 2 times 9 minus x to the positive 1/2 if I move that around. And on the top, I'm going to have 18 minus 2x minus x. So I end up with 18 minus 3x. Okay. Remember that sometimes we need to get a little bit fancy with our factoring because there's not much else we can do with that 1/2 power. So that gets us to here, which is not terrible. Second derivative is not so nice. So now if we want to find f double prime of x, now we have a quotient rule with a chain rule in it, which is not lovely. So what we have here is the derivative of the top, which is going to be negative 3, times the bottom left alone, which is 2 times 9 minus x to the 1/2 power. Now we have minus the derivative of the denominator, which is going to be 1/2 times 2, which is 1, times 9 minus x to the negative 1/2 power. And then times the derivative of the inside, which is, again, negative 1, and then times the numerator left alone, 18 minus 3x. Ugh. And that's just the top of it. Now the bottom of it is going to be the denominator squared, which is going to be 4 times just 9 minus x, because 1/2 power raised to the second power, you multiply them, we just get 1. So that doesn't work out half bad. Okay, let's see what we can clean up here. I've got a lot of factors that seem like they can match. So I'm going to go ahead and multiply out the coefficients first. You might be able to pick and choose the pieces that can come out. I'm just having a hard time collecting what I've got, so I'm going to go ahead and do this. Let's see, now I've got plus, and I also know that I can factor a 3 out of this guy. So I'm going to go ahead and do that. I'm going to factor out a 3. So that gives me 9 minus x to the negative 1/2. The negative 1, change that to a plus, so I've got that. And I took the 3 out of this, which makes it 6 minus x. Whew. And that's all over 4 times 9 minus x. Now, just like before, let's look at what we have in terms of a common factor. We can factor out a 3 from both of these. And again, we can factor out a 9 minus x to the negative 1/2. So that leaves us with negative 2 times 9 minus x to the first power, for the same reason we talked about before, plus all we have left here is 6 minus x. Well, that's not awful. Over 4 times 9 minus x. Let's rearrange what we can now. And so we have on the top, the 3 is going to stay put. The 9 minus x to the negative 1/2 is going to move to the bottom, and then I can multiply it by 9 minus x to the first. So when I add those, oops, the 4 is still there. When I add those powers together, I get 3/2 times, this is going to be, I'm going to do a little scratch work here, negative 18 plus 2x. So now I can combine those, and it looks like we get x minus 12. And so I believe that that is our second derivative, which, yuck, but we're done. So what were we doing? We need to find our possible points of inflection. So we want to look at where does the numerator equal 0, where does the denominator equal 0. So f prime of x equals 0, or f double prime, I'm sorry, equals 0 when x is equal to 12, because that's when the numerator is equal to 0. F double prime of x does not exist, it's undefined, when x equals 9, because that is when the denominator is equal to 0. So those are possibly two of our potential points of inflection. The reason why I say possibly is because that original function f of x has a square root function in it, a square root piece in it. So we need to think, remember the domain here is going to be anywhere that 9 minus x is greater than or equal to 0. So if I add x to both sides, that tells me that x has to be less than or equal to 9. That is the value of our domain. Nope, I'm sorry, I've got that backwards. Let me not try to do too many steps at one time. If I add x, I get 9 is greater than or equal to x. No, that's right. So x has to be less than or equal to 9. Okay, the reason why this matters is because if the x's have to be less than or equal to 9, then this value of x equals 12 is irrelevant because it's not in the domain of the function. So all we need to be considering then is, since it can be less than or equal to 9, 9 is where the domain of the function stops. That's also our only possible point of inflection. So we need to test something to the left of 9. And there's going to be nothing over here because that's outside of the domain. I like the number 0. If we plug in 0 to, f double prime of x, we should get a negative value when we do that. And that is because the function is concave down on negative infinity to 9. If you don't believe me, the graph of the function looks something like this. Here's 9, and it goes like this. That's what the graph looks like, which is concave down all the time. So that one is kind of ugly, but I wanted to make sure we walked through a derivative like that. So we'll look at parametrics in the next example.